So today we've got 13, maybe, well, 13 plus 1, maybe 12 plus 1 if number 3 doesn't turn up. Lightning talks. Everyone's got 1 to 3 slides to give a 2-minute talk about their poster, to advertise it for you, to encourage you to go and chat with them about their poster and vote for them in the poster competition later today. Basically, they will come up, they will talk. When it gets to 30 seconds, I will show them the 30 seconds sign. If it gets to 0 seconds, I'll start clapping, you'll join me, and we'll move to the next person. So I think Kirsty is the first one up.
Hello. Oh, it's very loud. Hi, my name is Kirsty Pringle. My poster is all about public engagement project that I've been working on, which is called the Air Quality Stripes. And what we've done with the Air Quality Stripes is we've taken inspiration from the Climate Stripes, which we've seen a couple of times already in this programme, designed by Ed Hawkins at the University of Reading. And what he did with the Climate Stripes is he tried to create a really simple visualisation which summarised the change in temperature of the planet. So it breaks all the rules in terms of a visualisation. It's got no numbers on it, but it is really engaging and it tells a really simple, clear story. So we've tried to do the same with the Air Quality Stripes. Unfortunately, air quality is a little bit more complicated in some ways because you have different trends in different cities around the world. So cities in Europe tend to have cleaner air quality than we had back in 1850. Cities, unfortunately, in Central Asia and Africa tend to have poorer air quality. So we have a story of different changing trends, basically, in air pollution. But we've taken some similar ideas from Ed and we've tried to kind of create some kind of visually attractive images which really explain the changes in air quality and exchange the story. It's really important. Air quality has a massive effect on people's health around the world. A lot of the illnesses caused by air quality happen in the global south, so we have a very uneven kind of exposure depending on where you live. The reason I wanted to bring it along to this conference is because it's interesting, it's quite fun, so come and talk to me about it, but also I have this kind of feeling that within a community, the research software engineering community has a huge amount to contribute to public engagement projects. We worked with RSEs to manipulate the data to create the website, and I feel it's not really celebrated, the role of the RSE in public engagement. So I'd really like to kind of start a conversation around that so we can kind of hopefully add it to the list of many, many things that the skills that RSEs have which can contribute to science and to outreach and hopefully to public engagement. Thank you.
Stop working. Technical issues.
Hello. So we are the RSC team from Tokamak Energy. So our company is dedicated to provide clean energy through nuclear fusion reaction. So nuclear fusion reaction is the one which powers the star. So we are trying to bottle up the star. Instead of plastic bottle, because we are sustainable, we are using magnetic field to confine them. So in nuclear fusion, like all the particles are in the fourth state, which is plasma, which is quite hot, some millions of degree Kelvin. So for comparison, in the surface temperature of the sun, it's like the core temperature of sun is 15 million Kelvin. So we have achieved 100 million Kelvin, and we are going to go beyond. In order to study the plasma, we have a lot of diagnostics, and in order to infer the diagnostics, we have a dedicated diagnostic analysis chain, which have to be run in a sequential order, and we call it as PPAC, and my colleague will explain more.
So our pulses are around a couple of 100 milliseconds. It's a really quick snap. We get tens of gigabytes of data for each and every one of these snaps. We want to be able to process that and analyze all of the data before the next pulse, which gives us 20 minutes to do a lot of sophisticated physics analysis. To do that, we require a framework. We require something that's scalable, that does all dependency handling, does error handling. So we built something like that, based on Slurm, HiPC computer framework that you might have used, and which replaced the old manual fork join implementation. This thing works, it's fast, it's reliable. If you want to hear more about how we did this, come see us at the poster later on. Thank you.
Hi, my name's Adrian. I'm from Imperial College, and I've got a poster about the HPC and RSE experience program that we've been running the last year and a half or so. It's basically an entry point for early career RSEs, maybe just finished their PhD or master's program. People that are interested in what is RSE or what is HPC system administration, and it's basically just this entry-level sort of 6-month job, work with the RSE team, work with the HPC platforms team at Imperial College, and yeah, introduction to what that's all about. This poster is basically just an invitation to come have a chat. Maybe you can implement something similar in your own institutions. We think it's a pretty good way to get people into the field and then also train up people that might go back into academia and you know, broaden the skill set and knowledge around these topics in the broader community. So yeah, come have a chat if you're interested.
Yeah, hi, I'm Cara, and I brought a poster about a project that I worked on a while ago, where we wanted to see what we could find out about the life cycle of a research software repository. So particularly how long they remain active for and how communities build around them. And so that we could hopefully learn from that data how we can build software that can survive beyond the length of a research project. So what we did was we developed a modular and reusable toolkit to first of all find and then validate links to research software in publications. And then we gathered data from the GitHub API about those repositories, so for things like commit stats, issue stats, who opens issues, who closes them, and when. And then we accumulated all that into these repository timelines together with the metadata from the publications so that we can see all the activity and events throughout the life of that repository. So obviously that's quite a lot to comb through, but I just wanted to highlight some very key observations. So first of all, we found that indeed repositories with 5 or more contributors have a much higher life expectancy on average of around 5 years than those with just 1 contributor. So that just shows that it's really important that we learn more about how we can build communities around pieces of research software. We also found that when issues and pull requests are left unanswered for a while, those repositories don't really gain new contributors, even though they might still grow the number of stars that they are able to collect. So maybe it makes sense to take some time to, you know, set aside some time to answer issues and PRs when you first publish software. And we also saw that if repositories are linked to later on in later publications, and that can lead to an increase in their visibility in terms of the stars as well. So for example, when they're reused or cited as related work. So yeah, if you're interested in a year in the life of a repository, come find me at the poster and let's have a chat.
Hello. Hello. Hi, my name is Cameron Peacock, and I'm a second-year PhD student at the University of Manchester. And my poster is looking at a simulation software called RivaSim, which is used to model evolutionary and ecological trends that we see within the real world. So RivaSim is an individual-based model, and the key benefits of these kind of simulations is at the high throughput, so you can generate a lot of iterations over a short period of time. It's implemented in C++, open source, available for download on GitHub, and it's also quite an extensive handbook online which looks at the various parameters and settings within the software. It's highly efficient, which means it can be run on relatively modest hardware, so I run it on a Mac, but it's also available on Windows and Linux systems. And the reason it's so efficient is that it's highly simplified, which means it doesn't take into account a lot of the parameters that we see within the real world. But the interesting thing is, despite this abstraction, we are still able to replicate a lot of the results, a lot of the trends that we see in ecology and evolution, which kind of gives credence to this idea that maybe these parameters aren't as influential as we once thought. And finally, it is very flexible, so each iteration can represent hours and days up to years and hundreds of years. So it's got a very broad scope in terms of what it can be applied to. Very quickly, I've been looking recently for my first chapter at replicating some of the results that you see within the literature. So for example, this study by Freestone et al. And as you can see, Rivasim was able to successfully replicate the results. And now what I'm currently looking at is trying to tease apart the mechanisms that are driving this. Thank you very much.
Okay, hi everyone. I'm Liam at the University of York Plasma Institute, and I'm here to talk about the Plasmafair project, which is aiming to improve the sustainability of software within the plasma sciences. We do this by offering free software engineering support to any scientists who request our services. And as our name implies, our approach is guided by the FAIR principles for research software. So we're trying to make this software findable, accessible, interoperable, and reusable. We work with a very broad range of software. One day we might be trying to improve the maintainability of some mature legacy code. The next day we might be trying to get some brand new code by a PhD student or a postdoc ready for publication for the first time. In either case, this might mean we're just doing something as simple as ensuring things are properly version controlled. It'll often mean adding tests, documentation, an appropriate build system. And of course, we will often just be jumping right into the code, making improvements where we can, and ensuring that software design best practices are in place as much as possible. So having done this for a few years, we've also been essentially doing a gradual survey of the software ecosystem within the plasma sciences, which I think has been very helpful because it allows us to determine where existing software is already out there, which may be used elsewhere to kind of prevent duplication of effort. And it's also allowed us to identify a few niches where just the creation of one additional tool can really help solve some commonly encountered problems throughout plasma science. So if you come and see our poster, it details a typical workflow for us every time we encounter a new project. And it also showcases some of the software we've worked on over the last few years and how that's helped the scientists that we've collaborated with. Thank you.
Hello, I'm Giacomo, and I'm going to present IVERS, the European Virtual Institute for Research Software Excellence, a project funded by the European Commission running from 2024 to 2027. Our consortium spans a group of research institutions, including 5 European science clusters. IVERS aims to ensure software is of high quality, sustainable, and recognized as research output. We are building a framework for research software excellence designed by and for the research community. The 3-tiered model we've adopted, analysis code, prototype tools, and research software infrastructure, allows us to tailor quality indicators to different software types and life cycles stages. A key output of IVERS is the Research Software Quality Toolkit, the RSQ kit. This is a community-driven knowledge hub that brings together best practices, tools, and services for assessing and improving research software quality. Most importantly, IVERS is the first nucleus of a network of individuals, groups, and organizations who have research software at their core. We aim to establish and formalize a durable network which will drive improvements in research software quality and recognition globally. In the coming months, we will launch a series of activities aimed at engaging the community to shape the IVERS network and expand the membership. To get involved, visit our website at ivers.software, join our community discussions, contribute to the RSQ kit, and participate in our upcoming events. Please come and talk to me and to Carlos Martinez and others here who are part of the IVERS project. Thank you.
Hello, my name's Dan. I'm from the University of Sheffield, and my post is about volcanoes. Specifically, some work I've been doing with volcanologists for about the past 18 months. They've developed hardware to measure sulfur dioxide from volcanoes. And they also developed some software to go with it, and I've spent the last 18 months sort of tweaking, improving, developing the software, making it a bit more usable for people outside of their research group. So if you want to hear more about what I've been doing, what I've found, what they found, how we've kind of worked together, please come find me. I've got pictures of volcanoes, they're very cool. Thank you.
That's yours. This is mine, okay. Hello, I'm Eli from the University of Manchester. Before I talk about what I work on, I want to talk about some of the common problems we face either as researchers or that the researchers we support face. If you're a data creator, you might ask questions like, how can I ensure people know how to reuse my data and workflows? If you're a data consumer, you might ask, how do I make sense of this data set I've just downloaded, which has 1,000 cryptically named files in it? And if you're more of a data architect, you might be part of a new large project, and you're trying to figure out how can we manage the data that we produce. All of these are, at least in part, metadata questions. RO-Crate aims to resolve some of those questions. RO-Crate is an open, community-driven, lightweight approach to packaging research objects with their metadata. If you want to know how it works, you'll have to come read the poster, but I'll share some of the benefits of it to draw you to come and look at the poster. First, RO-Crate is easy to include alongside your current data. You add a metadata file next to your existing data, and you distribute them together, and it doesn't really care what type of data you've got. RO-Crates are easy to consume because they use a standardized and interoperable format that's already supported by a few different platforms. And RO-Crate can work with your data. It has a very general base specification, but people are building, community members are building custom profiles for their particular domains. So there is a profile for tracking provenance of workflow runs. There's a profile for describing data in trusted research environments, and so on. And anyone can create a profile to support their own work. And the real power of RO-Crate is that it uses linked data. Again, if you don't know what linked data is, you can come and ask me about it. But basically what it means is that RO-Crates using this type of metadata are naturally interconnected with other RO-Crates and resources on the wider web. Thank you.
Hi, my name's Ricky Olivier. I'm from the University of Exeter, where I'm an RSC in the Research Software and Analytics group. So my poster is about creating greener software. Now, green computing is a wide encompassing term, kind of encompassing a whole bunch of endeavors to kind of reduce the carbon footprint of computing in general. For instance, it's estimated the ITC sector contributes about 2% of global gas emissions, possibly even more than the aviation industry. Now, obviously, software direct or indirectly influence the energy usage of the hardware it runs on. So creating green software is more than just optimizing your code. It kind of touches on various aspects of the software development process, which I'm trying to illustrate in my poster here. So there's a plot just that I generated for fun, so some specific recursive algorithm, and comparing 3 different languages. And there's some published studies on the energy efficiency and the carbon footprint of various languages. And the most popular ones are, as you expected, probably not the most energy efficient. And then also, obviously, nowadays with AI and machine learning, some deep learning models use a large amount of energy to reach a reasonable amount of accuracy. And if you even want to halve that amount of accuracy, you typically need to use 5,000 times more the compute power. So this kind of raises the question again in terms of what is your user requirements in terms of accuracy. So in the poster, I've listed 3 kind of broad categories which you want to consider in terms of what you need to do to create more greener software. And I've also in the poster added various links and references for more information. I'm hoping to meet similar RSEs with a similar kind of interest, and I'm looking forward to the Birds of Feather session on Thursday. Thank you.
Hello, I'm James. I'm from the UK Atomic Energy Authority, and we primarily focus on research into fusion energy, and this involves running a lot of different simulations. And to address essentially a problem we found, which is how you keep track of what you have run, where this data came from, and how you fed this through further simulations, we created SimView to keep track and manage all this data. It's also then used to manage the actual running of the simulations themselves, not just the data they produce. For example, creating centrally defined rules to stop them early, to more efficiently use your compute resources. We then found out, well, this was more useful beyond just the industry we started in. So for example, here, we're using it for fire simulations. So in this case, we have a problem where you have a room and you want to position 2 sprinters in that room such that you can essentially extinguish fires as quickly as possible. So we have a large parameter space to search. And so what we have defined is an interface where you can define an optimization strategy, a way of searching a parameter space for an optimal point. Now, to investigate any given point requires you to run an intensive simulation, which takes a long time, lots of electricity, and just slows down your whole pipeline. So ideally, you want to run as few as possible. And so we try to define more efficient optimization strategies than just a simple grid search, which would just sweep across all your parameters. For example, we have a Bayesian optimization one, which essentially uses the result of your previous ones to determine which points are more promising to investigate to find more optimal solutions, reducing your overall number of simulations you need to run, so you're more sustainable both economically in terms of the money you're spending on your electricity and your compute resources, and also in terms of green computing. And also, because there's such a trivial interface, it's allowing more industries to use this software. Thank you.
Thanks. Hi, everybody. I'm Toby from the Carpentries. So the poster that I've got this year is introducing a relatively new training program from the Carpentries. The Carpentries is a global community teaching software and data skills. We teach and certify people with an instructor training program. Are there any Carpentries instructors in the room? Cool, yeah, that was nice. And so the collaborative lesson development training is designed to kind of complement that instructor training that teaches people how to teach effectively, to also tell you how to write lessons that can help you use those skills to teach things effectively. We know that there's a lot of demand out there for training beyond what the Carpentries can offer, and I know a lot of people in the room are developing their own lessons, potentially using the open source infrastructure that Carpentries provides. And so the training is really about trying to help you do that more effectively and have kind of best practices in curriculum design and open source development and collaboration and so on. You can come visit the poster to learn more about what's in the training and how it's delivered and stuff like that. You can ask me questions about it, and I will also offer you stickers too. So there's an extra incentive. Thank you for listening. I'll hand you over to the next person. Thanks, sorry.
Hi, I'm Deepak. I'm from University of Cambridge. I'm here to talk about the poster in which we are presenting how we have optimized a nuclear fusion application. For those of you who are new to nuclear fusion, it's the same process which powers the sun, but what we are doing here, we are trying to artificially create the sun on Earth, and that is very computationally intensive. So we have already listened about what plasma is from Tokamak Energy. So we are trying to model the plasma. And in the process of doing so, there are a lot of processes involved, and which requires us to computationally model all the processes. And this particular work that we are discussing in this poster talks about a particle tracing code which models something called runaway electrons, which are very essential to be modeled so that the material inside these big machines don't get damaged and we don't have a lot of downtimes in these machines. So you can think of runaway electrons like marbles falling from a hill, And they based on from where they are starting, they'll have different trajectories. And each of them will have their independent motion. And so we are here highlighting how, we are highlighting how, using simple techniques. So we started with this code, which was a legacy, we were using a legacy compiler. And so, we ported the application from legacy compiler to the modern, Intel Food compiler. After doing that, we could profile the code successfully. And when we got the profiling result, we were very surprised to see the time which the code was spending in the I/O operation. So finally, the takeaway message is we could achieve around 50x performance for multiple runaway electrons. And yeah, and please do visit the poster. Sorry. Yeah.
Finally, we have a video from a poster presenter who had a last-minute inability to come to the conference, so they're attending remotely. Several of their co-authors are at the conference, and one of them will be by their poster at the poster session later today.
Hello, everyone. My name is Surbhi Goel, and I am briefing you about my poster on streamlining ML packaging. For the poster, we have used a case study to implement good practices of writing machine learning code. It is one of the projects that ICCS is working on, and it is an ML-based emulator of an atmospheric process called gravity waves. In this work, our focus has been on implementing fair software engineering practices by enforcing various coding standards. These standards are in the form of practices like using a version control system like GitHub, adding adequate documentation to the code, making the code as modular as possible, etc. For enhancing the interoperability, we use an open source interfacing library called FTorch in conjunction with the ML code that facilitates the flow of data from a Fortran based source code to a PyTorch based model. In conclusion, the practices will benefit both software engineers and researchers to develop reliable and ethical machine learning applications. Thank you so much for your attention, and I am available online on the platform Canopy for any poster related queries. Thank you.
Yeah, so I think the reason this failed was because they didn't open it in Google Slides. Anyway, the poster and drinks reception is at 5:15 in the main atrium. We'll be moving the poster boards to the general area so there's more space around them. You're encouraged to speak to poster presenters there to decide who you want to vote for in the poster competition. If you're unable to attend the in-person poster session, you can ask questions on Canopy. Each poster has their own page with the Q&A section. We've asked poster presenters to keep an eye on this and try to respond to any questions. So please remember to vote in the poster competition. The prizes have kindly been sponsored by Cloudcubed. The voting will close at 6:15, the end of the poster session, after which the top 6 posters from the attendee vote will be judged based on the original call criteria: accessibility, creativity, and a third one I can't remember. And from there, we will decide the top 3 posters who will be awarded at the awards ceremony tomorrow. Thank you.